Hey Raiders, let's take a look at some basic forces, Newton's laws of motion problems. And before we dive in, just a couple of reminders. Remember that force is a vector, and like any vector, that means you have to take into account magnitude and direction. So you'll see as we go through these problems that after initially identifying what forces we're working with, once we start substituting values in and doing calculations, we use positive and negative signs to show direction. So direction matters. And then the other thing to remember is that either or test. Every single object you analyze from the forces perspective, either it's going to be in equilibrium or it's not. So that pretty much gives you your starting point of either F net equals 0 if it's in equilibrium, all the forces in a different direction will cancel out, or the forces are unbalanced, they do not cancel out, and F net equals ma. So in some way, shape, or form, in the horizontal and vertical direction, one of these things is going to have to be true all the time. All right, with that said, let's take a look at number one. A net force of 250 newtons accelerates a bike and rider at 2.3 meters per second squared. What is the mass of the bike and rider? So this is pretty straightforward, as you can imagine, for the beginning ones. So as soon as you see any reference directly or indirectly to accelerating, there's your either or test. Okay, we have unbalanced forces. F net equals ma. So we can set up F net equals ma instead of F net equals 0. And if you look, what we're looking for is the mass, so that's our unknown. And they give us the net force, 250 newtons, and they give us the acceleration. So pretty straightforward. Divide both sides by the acceleration. And then the mass ends up being about 108.7. And remember, the base unit of measurement in physics is the kilogram. So there we go, 108.7 kilograms approximately. Okay, number two, how much tension must the rope withstand if it's used to accelerate a 1,000 kilogram car horizontally at 1.2 meters per second squared? Ignore friction. Again, earlier problems, we don't have to worry about friction at this point. So probably should have done the first problem as well, but let's just take a look at a basic free body diagram. So we've got our car. Don't be jealous of my skills. I've been doing this for years. You'll catch up. Pretty good drawing. All right, so here's where just a quick look at the free body diagram just to highlight the fact that force is a vector and direction matters. And remember, we've already learned that perpendicular vectors act independently of one another. So since we're analyzing horizontal motion, the vertical forces don't actually matter, but just as a general overview in the beginning stages here, we know that no matter which way an object's moving, gravity wants to pull it straight down. So force of gravity or force of weight, however you prefer to call it. In response to that weight of the car pushing down on the ground pushes back with that reactionary normal force. And then we're going to have our force of tension from the rope. If you want to generically call it F sub A for applied force, the force being imposed on the car, that's fine. But if it's moving to the right, we know that friction always opposes motion, so force of friction is to the left. So in terms of this free body diagram here, we're analyzing horizontal motion, so the weight going down and the normal force going up, those are perpendicular to the line of motion, so we don't have to directly worry about those. And then friction, it says ignore friction, so it does exist, but for our purposes for this problem, we're not worried about it. So, but once again, you can see a reference to acceleration, so there's your either or test. It's either in equilibrium or it's not. So horizontally, it is not in equilibrium. Vertically, it is in equilibrium. The weight will be equal and opposite to the normal force, F net equals 0 in this direction. But in the horizontal x direction, it's accelerating, so F net equals ma instead of F net equals 0. Now, remember what net force means. Net force isn't one specific force. It's the combined effect of all the forces acting in whatever direction you're talking about. So for us, it would be the force of tension plus the force of friction. They're going to battle it out, and they're going to be responsible for this 1,000 kilogram mass accelerating at 1.2 meters per second squared. Now, because this is an early problem, and they said ignore friction, we don't have to worry about that. So force of tension is just 1,200 newtons. All right, if you look at number 3, the purpose of number 3, what is the weight of a 66 kilogram astronaut on different locations? And the purpose of this problem is just to make sure you understand the physics distinction between mass and weight. In everyday life, we tend to use those words interchangeably. Like it's pretty common to say, oh, this astronaut weighs 66 kilograms. But in the physics world, we don't do that. Mass is the amount of matter the object has, and it doesn't change whether they're on Earth, the moon, or some other place. But weight, an object only has weight if gravity's acting on it. So you have to factor in what is the gravity wherever the object is. So this one's very straightforward. It's really just designed to make sure you understand that distinction between mass and weight. So what is the weight of a 66 kilogram astronaut A on Earth? So force of gravity or force of weight, whatever term you prefer, the bottom line, you calculate it the same way. You take the mass in kilograms and multiply it by the gravity it's subjected to. So 66 kilograms times gravity of 9.8 meters per second squared. So this 66 kilogram mass astronaut would weigh 646.8 newtons on Earth. Now notice here, we talked about force being a vector quantity and direction matters, and all year long we've been really emphasizing that, and the convention is up as positive, down as negative, but then I proceeded not to make this negative. We've talked about this in conversation when you're identifying a force like in a bubble and you're not really doing calculations with it. You know, someone wouldn't say they weigh negative 200 pounds. They would just say they weigh 200 pounds. So that's why I didn't put the negative sign for gravity, even though gravity pulls down and the weight. If we were doing calculations with this number, then we would have to take into account directional positive and negative signs. Okay, part B, same astronaut, so their mass is the same, but now they're on the moon where the effect of gravity is only about 1/6 of what it is on Earth. So to get their weight, that same 66 kilogram mass person, now only subjected to a gravitational acceleration of 1.7 meters per second squared. So they would only weigh 112.2 newtons on the moon, even though their mass is the same. And then Mars has a little more gravitational pull than the moon, but still less than the Earth. So they're going to be 66 times 3.7. So they weigh 244.2 newtons on Mars. And then D is designed to force you to kind of think about some other concepts here. What is the weight of the astronaut in outer space traveling at a constant velocity of 20 meters per second? So they're trying to make sure you deal with the fact that they could be moving. However, the assumption you have to make here when it says in outer space is you can assume they're kind of out in the middle of nowhere and they're not subjected to any gravitational pull. So in that case their force of gravity or their force of weight, again, they still have the same 66 kilogram mass, but they're not experiencing any gravitational acceleration, so they would be weightless. So it doesn't matter that they're moving. You know, that could have been from some previous situation, some outside force had, made the astronaut move at 20 meters per second. And when they're out in space, if there's no gravitational pull on them, there's no air resistance, there's no outside force to make them change how they're moving. They're just going to keep on going at 20 meters per second. Okay. Number 4, a 25 kilogram box rests on a table. What is the weight of the box and the normal force acting on it? So again, our free body diagram showing all the forces that are acting. 25 kilogram box. Got the force of gravity or the force of weight going down. Mass times gravity. 25 times 9.8. So this box weighs 245 newtons. And here's where the basic concepts of forces, Newton's laws of motion kick in, that luckily, I think most people have a pretty good ingrained sense of these things because we experience it in our everyday life. So we know in response to the weight pushing down on the table will push back with that reactionary normal force. And we know it has to be equal and opposite to the weight of the box. Because if the weight of the box were more than the reactionary normal force of the table, you just broke the table. Well, that didn't happen. So we know that's not the case. If the normal force were more than the weight, if the table pushed back with a force that was more than the weight of the box would accelerate up, which we know is not happening. So the only other possibility is equal and opposite. So going back to that either or test, either an object's in equilibrium in a certain direction or it's not. Well, it is in equilibrium. If we stick with the convention of up is positive, down is negative, 245 newtons plus negative 245 newtons equals 0. All right, so what is the weight of the box and the normal force acting on it? Well, there's the answer to A. Now B. Now we put a 10 kilogram box on top of the 25 kilogram box. Determine the normal force that the table exerts on the 25 kilogram box and the normal force the 25 kilogram box exerts on the 10 kilogram box. So it's kind of a mouthful, just take it one bit at a time. So first things first, determine the normal force that the table exerts on the 25 kilogram box. So we're looking at this contact here. So from the table's perspective, it has 35 kilograms pushing down on it. So the force of weight that it's dealing with is 35 kilograms times the effect of gravity. So from the table's perspective, it has 343 newtons of weight pushing down on it. So the table pushes back with a reactionary normal force equal and opposite 343 newtons. And then they shift the focus a little bit. Determine the normal force the 25 kilogram box exerts on the 10 kilogram box. So now we're zeroing in a little bit. Now we're focusing on this location here. So from the perspective of the 25 kilogram box, it only has 10 kilograms above it. So here's the 10 kilogram box on top. So it only pushes down with a weight of 98 newtons. So in response to that, the top of the 25 kilogram box, it doesn't have to resist its own weight. The table's doing that. It only has to resist and counteract the weight of the 10 kilogram box above it. So the normal force there is 98 newtons from the perspective of the 25 kilogram box. All right, number 5. What average net force is required to stop a 1,200 kilogram car in 8 seconds if it's traveling at 100 kilometers per hour? So a couple little wrinkles we got to deal with in here. First, notice parenthetically what average net force. This is basically just an acknowledgement that when you're hitting the brakes and stopping a car, you don't have to apply the exact same force to the brakes every single instant. It can fluctuate a little bit. But, you know, when you're doing calculation-based problems, when you see average, certainly that can make you kind of instinctively think, oh, average, add up the, a bunch of numbers and then divide by how many there are to calculate an average or mean. We don't have to do that. Just an acknowledgement that the force used to stop the car doesn't have to be this exact same every instant. So if you're going to stop the car and it's already going 100 kilometers per hour, well, there's your either or test. Either the object's in equilibrium or it's not. So while they don't directly use the word acceleration for F net equals ma, we know the car is accelerating, so we know we're going to be doing F net equals ma. And then just another little wrinkle, when you see the units of kilometers per hour, we got to be consistent with our units. The base unit of measurement of velocity in physics is meters per second, so we got to convert this. So we've already done this year, so we'll just do the quick version. If you just do 100 divided by 3.6, that'll convert it to meters per second. So that's about 27.8 meters per second. Okay, now, so let's take a look at what we're trying to do here. Let's jump right to our answer. What net force, so we're looking for this, is required to stop this car? So we know the mass, 1,200 kilograms. So the only other thing we need to know is the acceleration of the car as it's stopping. Once we know that, multiply it by the mass, we're done. There's our net force. So here's a recurring theme that's going to show up in the next few problems. We don't have enough information to work with. As easy as Newton's second law is, F net equals ma, we have one equation, two unknowns. We don't know the car's acceleration rate as it stops, and we don't know the net force. One equation, two unknowns. We can't solve it. So if you think about what we did earlier this year with kinematic equations, there was a variable in there, acceleration, that also shows up in forces. So it's not unusual. You have to do a little kinematic analysis of this car's motion to get its acceleration, which we can then substitute over into the forces equation. So that's what we're going to do right here. So let's look at what information we're given. So this velocity of 27.8 meters per second, that's the car's initial velocity, 27.8 meters per second. The final velocity, the car is stopping, so the final velocity is 0. and it happens in 8 seconds, and we want to find acceleration. Well, if we look at this combination of variables, that'll set up for using VF equals VI plus AT. So we'll substitute our values in. So basically, if you look at what's happening, the car's velocity is decreasing by 27.8 meters per second in the span of 8 seconds. So divide both sides by 8. So the acceleration rate of the car ends up being about negative 3.47 meters per second squared. That's the rate it has to slow down at over the 8 seconds to go from 27.8 meters per second to 0. So this acceleration rate, we can now substitute over here in F net equals ma, Newton's second law. So a 1,200 kilogram car accelerating at about negative 3.47 meters per second squared. So I'm going to put the negative sign in parentheses, 4,166.7 newtons. So I put that negative sign in parentheses just as a little reminder that when we talk and we communicate, we don't refer to, someone weighing negative 170 pounds. We just say they weigh 170 pounds. Same thing with the force here. What force is required to stop the car? It's a 4,166.7 Newton force. Mathematically, it is negative because it's working against the car's motion, so it's correct, but it's just in terms of how we would talk. We would say, hey, it was a 4,000 Newton force. Moving on. What average net force is needed to accelerate an 8-gram pellet from rest to 170 meters per second over a distance of 0.75 meters along the barrel of a pellet gun? So notice in this problem, you'll see a lot of reference to types of quantities that we worked with in kinematic motion, with our kinematic equations. So that's usually an indirect sign to you that you're going to have to do something similar to what we just did in the last problem. Analyze the object's motion to get its acceleration rate, which you can then substitute in a Newton's second law, F net equals ma. So if we think about the pellet here being fired from this gun, they want to know what the net force is. That's what we're looking for. And we already know the mass, but again, we got to be consistent with the units. 8 grams, well, there's 1,000 grams in a kilogram, so 8 grams, there's 1,000 grams in a kilogram. So basically, you just take the 8 and divide it by 1,000. So you're going to get 0.008 kilograms. And just thinking informally, every time you move a decimal one place to the left, it's like dividing by 10. So notice this decimal moved 1, 2, 3 places to the left. It's like dividing by 10 3 times, because 10 times 10 times 10 is 1,000, dividing by 1,000. So we're going to use Newton's second law, F net equals ma. We want the net force. This is what we're looking for. We know the mass, 0.008 kilograms. So we just need the acceleration rate. So once again, we'll analyze the one-dimensional motion here. So the pellet goes from rest. Well, so that's its starting point because it's from rest. So that means the initial velocity is 0. And then by the time it leaves the gun, it's going 170 meters per second. So that's the final velocity, 170 meters per second. And it happens over a distance of the length of the barrel, 0.75 meters. So from here, this combination of variables sets up for VF squared equals VI squared plus 2AD. Substitute our values in. Excuse me. 170 squared equals 0 squared plus 2 times the unknown acceleration rate times the displacement of 0.75 meters. So 28,900 equals, and this is 0, plus 1.5a. Divide both sides by 1.5. So we get a really big acceleration rate here. 19,266.7 meters per second squared. So certainly, as we reflect on our values as we go, this should make us pause and say, wait a minute, that's a really big acceleration relative to what we're normally dealing with. And that's a good reflection. But if you think about what's going on here, you're taking a pellet and firing it from a gun. That's a pretty explosive thing to do. So to make it go from being stationary to going really fast, 170 meters per second, that's basically almost 2 football fields a second. To make it go from not even moving to going that fast over a short distance of 0.75 meters, it has to have a really big acceleration rate. So it's good to reflect on that, but with reflection, that should kind of make sense. So the force is still going to be relatively small because it's such a small massed object. So the mass of 8 grams, or 0.008 kilograms, times that acceleration rate of 19,266.7. So the force is approximately 154.1 newtons. All right, take a look at number 7. A fisherman yanks a fish out of the water with an acceleration of 4.2 meters per second squared using a very light fishing line that has a test value of 20 newtons. The fisherman unfortunately loses the fish as the line snaps. What can you say about the mass of the fish? All right, so let's draw a free body diagram here. And it's gonna look like we're gonna hit a little bit of a stumbling block, but we'll have a solution to that. So we know that the line is pulling the fish up. So anytime a rope is applied through a force or a chain or a cable, we generically call that F sub T for force of tension. But certainly if you wanted the more generic F sub A for applied force, that's fine. But the bottom line is 20 newtons. And we know, regardless of whether or not object's stationary, moving up, down, left, right, whatever, gravity wants to pull it straight down. So the force of gravity or force of weight, mass times gravity. Now here's where it looks like we run into a little bit of a stumbling block because we don't know the mass. But we do know the effect of gravity, assuming we're here on Earth, 9.8. So we're going to have an expression for the fish's weight. It's going to be unknown mass times 9.8, or 9.8 m. That's our expression for their weight. And so we see the word accelerate. So the either or test, either the object's in equilibrium, F net equals 0, or it's not, F net equals ma. We're going to use Newton's second law, F net equals ma. So the net force is the combined effect of all the forces acting in whatever direction you're analyzing. We're analyzing the vertical motion here, so both of these forces apply. So the force of tension plus the force of weight, they're going to battle it out to make this fish of unknown mass accelerate at 4.2 meters per second squared. So if we stick with the convention of up is positive, down is negative, notice I just generically listed the forces that are going to combine for the net force without taking into account direction. But now that I'm substituting in specific values, now I will actually acknowledge, hey, force is a vector, direction matters. So force of tension, up is positive, and then the force of weight against that is negative, so it's plus negative or just minus 9.8 m equals 4.2 m. So notice what looked like it might have been a problem, we couldn't actually get the weight of the fish. It's going to be fine because the one unknown we're going to be able to solve for. So we add 9.8 m to both sides. So 20 equals 14m. Divide both sides by 14. So we get a value of about 1.43 kilograms. So in terms of tying this back to the question, now the line snapped. So basically what this means is the fish mass is greater than 1.43 kilograms. That's why the line snapped. Okay, take a look at number 8. .14 kilogram baseball traveling 40 meters per second strikes a catcher's mitt, which, in bringing the ball to rest, recoils backwards 9 centimeters. What was the average net force applied by the ball in the glove? So once again, you see a bunch of references to the motion of the object. So we're probably going to have a situation like we did in 5 and 6, where you're going to have to do some kinematic equation analysis to figure out the acceleration of the object. So let's see. So the ball's mass is expressed in kilograms, which is what we want, but the distance the glove comes backwards, 9 centimeters, we're going to have to convert that to meters to be consistent with our units. Well, there's 100 centimeters in a meter, so we can do 9 divided by 100. So that's the same as moving the decimal 2 to the left. So this is 0.09 meters. So again, they don't directly use the word acceleration, but if the ball was traveling at some velocity and then it's brought to rest, it's stopped, it accelerates. So the either or test, it's either an equilibrium or it's not. It's not. So it's F net equals ma rather than F net equals 0. And we know the mass, 0.14 kilograms. And so we're going to need to know the acceleration in order to get the force. So recurring theme here, we're going to do some kinematic equation analysis given the initial velocity is 40 meters per second. It's going to be brought to rest, so final velocity equals 0. And it happened over a distance of 0.09 meters. We're trying to find acceleration. So this combination of variables sets up for VF squared equals VI squared plus 2AD. 0 squared equals 40 squared plus 2 times the unknown acceleration times the displacement of 0.09 meters. So 0 equals 1,600 plus 1.8a. Subtract 1,600 from both sides. Negative 1,600 equals 1.8a. Divide both sides by 1.8. Oh, excuse me, that's a little typo there. This is So I said this is 1.88. 2 times 0.09 is 0.18. Sorry about that. So negative 1,600 divided by 0.18. Once again, we get a really big acceleration rate, and that should initially make us a little nervous here. The acceleration is about negative 8,888.9 meters per second squared. So we should certainly pause at that, but kind of like we talked about with the pellet in number 6, this baseball is going really fast, 40 meters per second, and it's brought to a stop in a very short distance. So that has to happen really quickly. So this acceleration can be substituted over here. So the ball's mass of 0.14 kilograms times this really big acceleration rate of negative 8,888.9. So we get, and I'm going to put the negative sign in parentheses, 1,244.4 newtons. Again, I put the negative sign in parentheses. It is mathematically correct because if we made the ball's motion the positive direction, well, then the force needed to stop it would have to be negative. So it's mathematically correct. But again, in isolation, we wouldn't say it's a negative 1,244 Newton force in terms of how we communicate. We would just say it's a 1,244 Newton force. All right, that's it for now. There'll be more later.